Alright, so we are back for the last section of Chapter 5. And in this section, we're talking about solving equations using exponential and logarithmic expressions. Um, so, throughout the course, we've talked about solving equations. We've used operations and inverse operations in order to help us solve equations. So we've gone over it before again, but we've talked about how addition and subtraction are inverse operations of each other, which help us to solve algebraically equations. We know that multiplication and division are also inverse operations. In the last unit, we learned how exponents, so if we have a to the n power, so the inverse operation of exponents of these exponents was radicals. So the nth root of a was the inverse operation of this. Well, here we have exponentials, not to be confused with exponents. Exponentials, which is a to the x, where the variable is in the exponent location. As opposed to exponents and radicals where your x was the base. So this is like kind of the reverse. But in any case, so the inverse of exponentials, as we've been talking about this unit, is logarithms. So a to the x, the inverse of that is, well, if we're going to be consistent with terms, we'd say b to the x is what we've been using. So the inverse operation of this would be log base b of x. Okay, so we are going to use this information and this knowledge of inverses to help us solve exponential and logarithmic equations. So for our first property, remember property is always important. If it says property, you're going to want to remember this. So the first property to help us to solve exponential equations, so we'll talk first about exponential equations, and then we'll talk about logarithmic, meaning that if we are given an exponential equation like this, we will essentially be talking about how we can solve for x if it's in this expression, and then we'll talk about it if it's in this expression. So first, exponential equations. So in algebra, the words read if b is a positive real number other than 1, so if b is something positive and not 1, then b to the x is equal to b to the y, if and only if x is equal to y. So to put that a little bit more into clear English and an example, I like to kind of show this in terms of geometry. So we, in SM2, hopefully you guys remember, or in geometry for those who took geometry, but in geometry, there's something that happens whenever you have two parallel lines. So say that we have these lines right here, and these are parallel. And this is a line that cuts through these two parallel lines. Well, what happens in this situation is that you create a bunch of angles that are equal to each other. So this right here, and this angle right here, is what we call congruent, or corresponding angles. And this angle right here is corresponding to this angle. This angle is corresponding to this angle. This angle is corresponding to this angle. So what corresponding means is that, see how this is the two parallel lines are, these two parallel lines intersect this line right here at two different locations. It intersects here and it intersects here. So relative to the two intersections, this corner is corresponding with this corner, meaning basically that they're in the same location relative to the intersections. So that's why they're called corresponding. Now, the corresponding angles are equal to each other. So this angle right here corresponds with this angle, so that means these two angles are equivalent to each other. and this angle right here and this angle right here, they're corresponding and they're equal to each other. Now, to kind of relate that to this algebraic equation, so you see how we have 3 to the x equal to 3 to the 5th power. So the x and the 5 are corresponding pretty much relative like to the location. You see that the base is the same number. Base is 3. So since the base is the same number, kind of like here, since this intersection have similar intersections, that means these angles are corresponding and equal, then that means these exponents are corresponding and equal. Because if we were to try and make this statement true, so if 3 to the x is equal to 3 to the 5, well, let's say, for example, let's say x was 0, so 3 to the 0 is equal to 3 to the 5. Well, that's obviously false. That's not true. So the only way to make this algebraic expression true is for x to be equal to 5. So that's why if 3x is equal to 3 to the 5th, then x is equal to 5. Okay, and we can use this to solve algebraic expressions. So here we can solve for x simply by stating that the exponents are equal to each other because their base is the same number. So x is equal to 5. And that's basically what this is saying, but in more simple terms. So let's use this in this example over here. So example 1a, we have an exponential equation. So this exponential equation, notice that the base is not the same. So this base is 100, while this base is 1/10. So that's kind of like the first thing you want to recognize is that for algebraic expressions, so for example A, you want the base, sorry, I totally spelled base the wrong way. You want the base to be the same. Or I guess we should say you want the base to be equal. You need the bases to be equal if you're going to use this property, okay? So solve each equation. So let's see if we can manipulate these bases to be equal to each other. So let's start on the right side. So this is 1/10. Now using properties of exponents, I know that I can rewrite this as 10 to the negative 1. 10 to the negative 1 is equal to 1/10. That's what negative exponents do. And I still have to the x minus 3. Now I have another property of exponent at hand, which is a power to a power, which means I can multiply the exponent. So I can multiply negative 1 with x minus 3, which means I get 10 to the negative x plus 3. So on the right side, I've created a base of 10. I've manipulated this side. I haven't changed the value of this side of the equation. I just manipulated it to have a different base. These are still equivalent statements. So on the left side, though, we have a base of 100. Is there any way that we can manipulate this to have a base of 10? Well, I know that 100 is the same thing as 10 squared. So I'll change 100 to be 10 squared. And now, again, I have a power to a power, which means I can multiply the exponents, so then I get 10 to the 2x. So now notice that on both sides of my equation, my base is 10, which is what I want. Now I can use this property of equality for exponential equations, which means that since the base is the same, so this is a base 10, this is a base 10, then that must mean that these exponents are equal to each other. So that means I can pretty much just ignore the base and just say that 2x is equivalent to negative x plus 3. So now I can solve for x. I just have a regular algebraic expression. So here I'll add x to both sides. So on the left side, this becomes 3x. Those cancel because they equal 0. And I'm just left with 3. I can divide by 3 on both sides. So then x is equal to 1. So I solved for x. If you were to plug 1 into these expressions, you should get a true statement. And that's what it means to solve equations using this property. Okay. Now for b, obviously we can't use this property because this is just 7 to the 1 power. So basically this is saying 7 to the 1 power. So this is a base of 2 and this is a base of 7. So we can't use this because the bases are not the same. So what we want to do here, this is still an exponential expression because it's 2 raised to the x power, which makes it exponential. So because this is an exponential expression, there's a different means of solving for this. I need to solve for x. So if I were to use these properties, that's what I need to do. I need to use what's called the inverse properties. Now, this right here on the left side is for exponentials. And on the right side it's for logarithmic, and we'll get to that, but let's first talk about the exponentials. So what this expression is saying right here, first of all, this says log base b of b to the x power. Now in the last section we learned that with the properties of logarithms that I can use a power property which allows me to move exponents to the front. So this is equal to x log base b of b. Now log base b of b, if the base and the argument are the same value, then this logarithm is equal to 1. So then this becomes x times by 1, which is just equal to x. So this is how we can use this inverse property when solving exponentials. So looking at this exponential, here we have 2 raised to the x power. Now the key here is taking the log of the base. So pretty much right here, this is a base of 2. Now if I on the left side do log base 2 of 2 to the x power, so on the left side I took I made it to log base 2. What this means is I also have to do that to the right side. So on the right side I also have to take the log base 2 of whatever is on the right side. Now this is okay because I'm doing it to both sides. I'm doing log base 2 on the left and log base 2 on the right. Now the reason why I chose log base 2 is because the base of my exponent is 2. So using the properties that we discussed last time, let me move this x over here. So this becomes x times log base 2 of 2. It's still equal to log base 2 of 7. Now log base 2 of 2, like we discussed up here, log base b of b is equal to 1. So this just becomes x on this side. So x is equal to log base 2 of 7. So this basically is like the equivalent of if you had something like 2x is equal to 7. So knowing that you know the inverse of this operation right here, since 2 is being multiplied by the x, I can divide by 2 on both sides. But we're using logarithms and exponents or exponentials, so that means if I want to eliminate an exponential, just take the log of it to eliminate the exponential. So that's what we did. We took the log base 2 of this left side, and we're just left with x when we do that. So therefore we get log, or x is equal to log base 2 of 7. And if you were to put this into your calculator using the change of base formula, you would get log of 7 divided by log of 2, and you get 2.807. Alright, and that's your value. Okay, so for B, use inverse property. Let me spell that correctly. Meaning, so this is an exponential equation, so the inverse property would be a log. That's what we did. We took the log of both sides. Okay. Now let's jump to this next page. And now let's talk about logarithmic equation. So up here was a property of equality for exponentials, and here's a property of equality for logarithmic equations, and they're pretty much the same thing. So right here in this statement, if we have log base 2 of x and log base 2 of 7, well then that means that if this is log base 2 and this is log base 2, so if it's a logarithm with the same base, then it must be that the only way for these two statements to be equal is if the arguments are equal to each other. So that means x must equal 7 in this case. Because if I say log base 2 of 3, well, that's obviously not equal to log base 2 of 7. You'll get different answers. So the only way to make this statement true is to set the arguments equal to each other. So this argument and this argument must be equal to each other. So let's use that in this first example. So for A, so following the same kind of idea here, you wanted the base to be equal, and here the base also has to be equal. So for A, same thing, base of the logarithm has to be equal. Okay, so here's what that means. So this is a natural log. Now, the natural log has a base of e. And here's a natural log, and the natural log is a base e. So these logarithms both have the same base. Now, since this is a natural log of 4x minus 7, this is the natural log of x plus 5, because they're equivalent to each other and they have the same base, then we can just take the arguments and set them equal to each other. So that means 4x minus 7 is equivalent to x plus 5. And so now we can just solve this algebraically. So I'll subtract an x from both sides, and I'll add 7 to both sides. So on the left side, 4x minus x is 3x. 7 and negative 7 is 0. X and negative x is 0. 5 and 7 is 12. I can divide by 3 from both sides, and I'll get x is equal to 4. There you go. So for B then, so again this is using the property of equality of logarithmic equations. Now on the right side, we're going to use inverse property. So that leads us back up to here. So this is the inverse property for logarithms. So logarithmic equations. So likewise, so over here, how we talked about log base b of b, this is equal to 1. Now over here, so look at this expression. We have b, raised to the log base b of x. So this right here is your exponent, and this is the exponential base. Okay? And this is equal to, this expression says that this is equal to x. So it's kind of the same thing as we talked about over here. If you have a log base b, so log base b of b is equal to 1. Similarly, if b is raised to the logarithm with base b of x, then this right here is just equal to 1. And you're just left with x. So that's how you get x. Okay, so that's how you can solve logarithmic expressions. So here we have for b the log base 2 5x minus 17 equal to 3. So if we're going to use the inverse property, then we want to take the base of an exponent, make sure that it's the same base as a logarithm. So what we do here, so this is a base 2. So on the left side, what I'm going to do is I'm going to do 2, and I'm going to raise it to the log base 2 of 5x minus 17. But because I did that on the left side, I also have to make the right side an exponential with a base of 2. So pretty much what I'm doing here is I'm taking the left side of the equation and the right side of the equation, and I'm turning them into exponents with a base of 2. Why I do that is because on the left side I have 2 raised to the log base 2, which means that these cancel. And I'm just left with 5x minus 17 equal to 2 cubed, which is 5x minus 17 equal to 8. And now I just have a regular algebraic expression. So I can add 17 to both sides, and I get 5x is equal to 25. I can divide by 5, and I get x is equal to 5. There you go. So for b, just like up here where we said use the inverse property, you'll use inverse property. This time though you'll use the logarithmic for logarithmics. So for logs pretty much. So we started out with a log, which means we use the log property, the log inverse. Up here we started with an exponent, or so this one you use the logarithm, right? Or I totally wrote this one wrong right here. This should be for exponentials. So use the inverse property for exponentials. And then down here it's for logarithms. So sorry about that. But yeah, we use the inverse property of exponentials, okay, because we're starting out with an exponential. And then here we use the inverse property of logs because we start with a log. Okay. Now let's do one more example of solving logarithmic equations. So this is going to be similar to up here, but just a little bit more difficult. So here it says to solve log of 2x plus log of x minus 5 equal to 2. Now, this is a common logarithm. These are common logarithms, which means they have a base of 10. Okay, so keep that in mind. So what that means is, what I want to do is I want to take well, first of all, first what I want to do, notice that because these are log base 10, then I can condense these logarithms using the product property because these are being added. So I'm going to use the product property of logarithms to condense these logarithms, which means I'm taking these two logarithms and condensing them into one logarithm. So using that property, this becomes log of 2x times by x minus 5. And this is still equal to 2. Now if I simplify my terms, I get log of 2x squared minus 10x, and this is equal to 2. So now I only have one logarithm. I have the log base 10 of 2x squared minus 10x equal to 2. So now I want to use an inverse property. So because this is base 10, I want to do 10 raised to the log base 10 of 2x squared minus 10x equal to, now because I use the base of 10, I have to use a base of 10 on this side, so 10 being squared. Now on the left side, these are inverse operations, so they cancel. So I'm left with 2x squared minus 10x equal to 100. Now, first of all, notice that everything has I can divide everything by 2. So I'm going to divide this by 2, divide this by 2, and divide that by 2. So I'm left with x squared minus 5x equal to 50. Notice here that this is an exponential, or this is a quadratic, not exponential. So this is a quadratic. And quadratics have two solutions. So I'm going to solve this like a quadratic at this point. So I want to make it so that it's equal to 0. So I'm going to subtract 50 from both sides. So then I get x squared minus 5x minus 50 equal to 0. And now I want to solve this like I would a quadratic equation. So I can use the quadratic formula, or I could factor. So I'm going to choose the factor. So I have x squared minus 5x minus 50. So I'm going to choose the factor. So because a is equal to 1, I'm going to have two binomial factors like this. And I need to find two numbers that multiply to be negative 50 but add to be negative 5. So negative 50, two numbers that multiply to be negative 50 and add to be negative 5 would be negative 10 and positive 5. So I'm going to do minus 10 plus 5, and then I'm going to take my factors and set them equal to 0. So I have x minus 10 is equal to 0, and x plus 5 is equal to 0. In this case, x would equal 10. Here, x would equal negative 5. So here are two solutions. Now we have to be careful. We have to check for any extraneous solutions. So we did this in the last section, in section 4. We have to make sure that these solutions still work if we were to plug them into this equation right here. So let's think to ourselves though, if we take the log of x and graph that, remember that we have a horizontal or a vertical asymptote at the y-axis, meaning that notice that this function, this blue function, only exists over x values greater than 0. This function does not exist for any values that are less than 0. So that means x values, or anything in the log, has to be greater than 0. So if I take, for example, 10, let's check 10 and plug that into our expression. Then I get log of 20 plus log of 15 equal to 2. Now we can always check this in our calculator. We can do log of 20. Did I say 15? I think that should be 5 because it's minus. So this should be log of 5 because I'll do 10 minus 5, and so that's going to be 5. So let's do log of 20 plus log of 5. So log of 20 let's try that again. Log of 20 minus log of 5, and it's supposed to be plus log of 5, so log of 20 plus log of 5. Sorry, what did I do this time? I didn't put in log of 5. Sorry, this is so difficult. So log of 20 plus log of 5. Okay, enter, and I get 2. So there we go. So this checks out. Let's try putting in negative 5 though. So if I do log of negative 5, so that means I get log of negative 10 plus log of 0, or negative 5 minus 5, so that would be negative 10 still, because negative 5 minus 5 is negative 10. So let's try doing log of negative 10. So log of negative 10, if I plug that in, do enter, you'll see that I get an error. And again, that's because I can't take the log of a negative number. Because if I go back to my graph here, notice that the log does not exist for negative numbers, the log function. So that means x minus 5 is not a function, or is not a solution. Only x equal to 10. Okay, now let's come down here, and now we're going to do the same thing, but we have inequalities. So this is an exponential inequality. So be thinking, remember we have two methods of solving exponentials and two methods of solving logarithms. So here's 1 and here's 2 for exponentials. For logarithms, here's 1 and here is 2. So this is an exponential. This is exponential. So I'm going to use, because this one doesn't have, this one's not being raised to any power, I'm going to use the inverse property of exponentials. So what I'm going to do is I'm going to take the log base 3 of 3x, which means on the left side I also have to do log base 3 of 20. So I have to take log base 3 of both sides. On the left side, these will cancel, and I'm just going to be left with x is less than log base 3 of 20. And that's really it. So if you plug log of 20 divided by log of 3 into your calculator, so log of 20 divided by log of 3, you get 2.727. So this becomes x is less than 2.727. There you go. That's really all it is. So this one's a number 6 is a logarithmic inequality. So I'm going to use, because only one side is a log, I'm going to use the inverse property of logarithms, meaning that, so this is a common log, so the base is 10. So I'm going to do 10 raised to log base 10 of x, and this is less than or equal to 10 raised to the second power. So I'm raising both sides of 10. Now on the left side, those cancel because they're inverses, so I'm left with x is less than or equal to 100. Now just be careful for inequalities. Remember that you can't take the log of a negative number. So that means x has to be greater than 0 also. So that would be your inequality from 0 to 100 is your solutions. Okay, now that will do it for the rest of this section and for this chapter. So look forward to be prepping for an upcoming test.